Okay, perfect. So hi everyone. So thank you everyone for the organization of this little talk. I'm very glad to be here to present the company and what we do. And at the end, if you have any question about what PREDISURGE is doing, feel free to ask. So my name is Florian. I'm working at PREDISURGE for 7 years now. And I'm the manager of the innovation team PREDISURGE, and what we call innovation, it's more like R&D tasks. So I supervise all R&D tasks about AI and also numerical simulation at PREDISURGE. So in the next around 30-40 minutes, I will share what we do at PREDISURGE, a little bit interesting the company also. And the idea is to have like an industrial point of view of the technology, how we assess the problems, and how we try to sell what we are doing. So the time of this session is from medical imaging analysis to risk-aware EVAR planning. So I will dig into EVAR planning, what it is. So yeah, we are dealing with the medical purpose anyway. So the agenda for this session. So first, I'll introduce the company so that you understand from where we started and what we are doing. And second, I will talk about the clinical challenges that we have. So I'll dig into the EVAR problem so that you can understand what the medical problem is and how we try to solve it and to improve it. Third, I will talk about the pipeline that we have. So from the really beginning of the problem with the image of the patient to the digital twin and how we manage to have value for the surgeons and physicians at the end for the medical clinical decision. Fourth, I will talk about the risk-aware planning. So the idea is when we have, in the medical point of view, when you have patients with some troubles, you try to find the way so that it minimizes the risk at the end for the patients. And finally, I will talk about how we deploy the solution once we have all the R&D stuff that are right and everything is working, how we manage to deploy and to make it available for the clinicians and the patient. So let's start with the company first, who we are. PREDISURGE, we are based at Saint-Etienne, so it's pretty close to here. And actually, we're just in front of the Saint-Etienne Châteaucreux. I don't know if some of you came by train. I think you couldn't miss the building. And so we are here. We arrived 2 years ago in those building. Before we were just close to here, this side maybe, at the GUC. Just close to it. And before that, we are at the hospital of Saint-Etienne, Saint-Priest-Saint-Germain. So we are now around 30 employees, mainly from the technical point of view. So it means that we have developers and many people on the research part in AI mainly, and also numerical simulation, digital twin. I will talk a little bit more about this. And we have also 3D computing. And the main point of what we are doing is about cardiovascular surgery. So we have internally Jean-Noël Bertini, which is a surgeon in cardiovascular, so which is helping us finding what is expected by the surgeons. And we are across 17 countries, mainly in Europe, for now in Europe. But we also have some research and development done for USA and South Korea, for instance. The reason why we don't have projects in there is because of medical purpose and medical regulatory. So that means that we have, I will talk about that later, but we have CE mark for everything that we can sell in Europe. And then for each country, I would say we have different norms to have, and then it makes it long and to deploy everything in the other country. But everything in Europe, usually can. So the mission that we have at PREDISURGE, the idea is really to enhance patients' outcomes by empowering physicians with AI and digital twin solutions for cardiovascular interventions. So what it means is that in cardiovascular fields, when we have patients, the idea is to have surgery in the patients to make them better. But physicians, based on their experience, they will find their best way to do the surgery with the right prosthesis, for instance, and the right methods from their experience, but they can't really see the future and how the risk will be resolved with the surgery that they have to do. So the idea of what we do is to like predict a little bit the future of the surgery so that the surgeons can see what's going to happen, what the risk they're going to have in the patients, and to anticipate and maybe change the way they will do the surgery. But at the end, we're just a tool, and thus the physician surgeons make the decision to apply to the patients. So today we have more than 300 clinical centers on which we help, and more than 1,050 patients that we've treated with the digital twin. Sorry. So last slide about the company. So we started in 2007. So it's like old company, but everything before 2017 was mainly research. So at the end, it was like a PhD session between, I think, 2014 to 17 that has proven that we can do numerical simulations to simulate the operation of surgeons. So the operation is called EVAR, and I will just talk about this just after. And at the end, so since it was good enough, so the Surgeon General decided to create PREDISURGE. And from now, so it's almost 10 years. From there, we done some few steps. So the first one, 2019, was the first clinical study that showed that the numerical simulation could be used to predict the end of the intervention of the surgeon with very good performance. And 2023 was a milestone also for us because we got some investors in the company from a bit more than 6 million euros. So that helps us for sure to employ people and to move faster on the topic. And then last year we have, and I will show it later, the full automatic process pipeline from the image to the prediction, the risk of prediction, fully automatized for the surgeon. Some numbers, so we have 14 patents, as I said, more than 1,000 patients simulated and CE marked products. And as I said, for the other country, we need like FDA for the US, so we are working on it, but it takes some time, hopefully this year. So yeah, we need to be RGPD compliant also, and some ISO, so this is for security. So yeah. So the clinical challenge, so what is EVAR first, and why we need to improve the process for the surgeon. So the main target that we have is for the aortic aneurysm. So I think everyone knows a little bit about aneurysm. Maybe we know more about cerebral aneurysm, but aortic is the same. So it's vascular disease in which the aorta is going to grow. Because yeah, the aorta is becoming old, and then in some patients it can grow, and the risk is that it grows so far that at the end we have some rupture, and if we have the rupture, then it's a disease, it's the death of the patient in most of the cases, unless you are already in the hospital with the surgeon above you, but it almost never happens. So it touches roughly around 5% and 10% of men above 60 years. So it's 60 years old. So it's mainly disease that comes with the age. But anyway, we have like 4 million people that may be involved. So to resolve this disease, there are 2 ways: the open surgery that I don't show here. So we can open the patient, and so it's very invasive. And as I said, patients are quite old. So when you open the patient and try to resolve this the aneurysm, then the patient, it's very difficult for him, for her to go well at the end. So what is done now, mainly like in 80% of cases, they do what we call EVAR, so endovascular repair. And so endo is for going from inside the vessel of the patient. So we don't open the patient. We try to put a stent, or prosthesis, like what you show at the top, inside the patient. So going usually from the iliac, from the legs, they go with like a wire, and they go up until the abdominal part, and they release this kind of prosthesis at the emplacement of the aneurysm, and then the blood flow only goes in the prosthesis and not anymore in the aneurysm part, and then it doesn't inflate anymore, and the patient is saved. So EVAR is like the simplest operation that we can have in the aortic point of view, because as you can see, the prosthesis will be just below some vessels or arteries that we have here. So it's simple because you don't have to take care of what those vessels will do if you block them with the prosthesis. I will show you some cases. So the aneurysm is exactly at the middle of the vessels, and then you need to think about the prosthesis to not block all the vessels. For instance, those two ones are for the kidneys. So if you remove the two kidneys, then it's going to be complicated also for the patient. Why is it EVAR planning still hard? So I'm just talking about the planification, not the surgery. So how do we prepare it? Like how do we select the prosthesis? Where will the prosthesis be released in the patient and everything? So this part is quite time consuming. First, for the surgeons, it takes around 1 hour for one patient. So to look at the images of the patient, measuring everything to get the prosthesis done by the manufacturer. And then there is a process of building the prosthesis, but just taking the measurements. Second, it's really operator dependent, which means that between two surgeons, we can have two different measurements and two different prostheses that will be selected, or maybe two types of operation, because one will decide to put the prosthesis just below the vessels and the other one really below. So we can have, it's really dependent of the experience of the surgeon. There is limited collaboration because for each patient, only the surgeon mainly will see the scan, and it's really difficult in the hospital to share the images to others. So usually they work alone. And then, as I said before, guessing the complication is very difficult because it's based on the experience of the surgeon. I will talk a bit more about the risk that we can have, but they can't predict the future. So they will say, okay, I will put the prosthesis here, but what will happen after, I don't know. Third, the pipeline of PREDISURGE. So really, how do we proceed from the image of the patient to the digital twin and the risk? So in one image, this is what we do. So first at the left, we have usually patient does like a CT scan. So it's really like usual for the patient, and more with the old patient, like more than 60 years old, it's often that they have some imaging procedure just to check or something else. So this is the kind of imaging that we have in clinical routine, and they see that there is an aneurysm, because usually they don't have like a clinical pathology that they will tell you that, okay, I feel that I have a aortic aneurysm. So just by imaging that you can check it. So we have this, and from this we build the aortic digital twin. So mainly it's a mesh. And then from the other side, so the surgeon will tell us which prosthesis he wants to put inside of the patient. So we have the real model here, and so we do almost the same thing with the image. We do a numerical stent, so it's a mesh also that we have, and at the end we put everything together to have the simulation. And so this visualization allows the surgeon to see what will be the results of the surgery. So of course here the aorta is specific to the patient. So for each patient we'll have different aorta. Also the prosthesis is not or specific to patient, but have like 100 prostheses, for instance. And at the end, so in the simulation, the prosthesis can move and have some material properties and have the shape of the aorta, and also the aorta is able to reshape itself because of the stents that is quite rigid. So everything is moving in the simulation. So first step about how do we obtain the aorta digital twin from the image. So the first thing is 3D image segmentation with deep learning. So when I arrived, like in 7 years at PREDISURGE, deep learning existed, but was not really used in the industrial point of view. So we had like thresholds, for instance, on the image. I don't know if you can see that was, yeah. So the outer part is the white part here. So the idea is to segment these parts to, at the end, obtain a volume and then the mesh on the outer. So to do this today, what you use is neural network. So I won't dig into a specific model we use and how we train, but just to have an overview. The idea is to train a model of neurons to, from the image, get this labelization. So we have the image, the ground truth. So we need to first annotate everything. That the painful part of the deep learning usually is that you have to have the image and also the annotation part, and then the neurons will learn how to go from this to this, and then from a new image, it's able to segment the new one to create the new masks. So the main key point that we have to be sure that the result is good is what we call the dice, and to measure the difference between the ground truth that has been annotated usually by experts, so surgeons, radiologists, and what the AI deep learning will infer the segmentation. And then so dice usually it goes from 0 to 100, and the more we close to 100, and the better the automatic segmentation is close to the manual one. So today, in the first segmentation that we did, we didn't have just one what we call label, which is called here we could see that the aorta, for instance, but we have three. We have the aorta, so what we call the flow lumen, which is really where the blood flow is moving, but it's inside the aorta. Then we have what we call the thrombus, and so in non-pathologic patients, there is no thrombus, and also there is no calcification, the last one. So it is more like a blood flow that has been coagulating, and that's one of the main code of, of the growth of the aneurysm. So this is the second label, and the third one is what we call calcification, which is here. And again, it depends on the disease of the patient, but it's more like almost little bones that are the outside of the aorta and makes it really rigid. So it has to be taken also into account in the simulation, because the aorta won't move at the same manner if we have a calcification or not. And so this is one of the results that we have, and we see that from when we overlay the segmentation and the CT scan, sorry, it's pretty well. So that was the first one. The first one was in 2023, and last year, sorry, 2024, and 1 year later, so we had this segmentation, which is close to the same area. We didn't change the area because what is interesting for us is really where the aneurysm is. But what we've added is more labels, and the more labels that we have, and the more it's difficult for the algorithm to learn every label and to understand which label is at which place. So here we have 14 labels, and what we have did is that we have one label per collateral arteries. So we have the like I told before, we have the renal arteries here, left and right. Maybe it's moving also. We have the lumbar artery, which are really small, and so to give you a rough idea, the lumbar arteries, it's close to 1 or 2 millimeters, so it's really small to detect even with the eye on the CT scan. And so we consider all the labels that we have. It's very important then for the visualization for the surgeon to know which artery is where and the size and everything. So just to give you a rough idea, but so the first was done with the 200 patients, roughly, the first segmentation with 3 labels. And here we have more than 400 patients for this segmentation. And we have, so the dice is 96%, which is close to, from the studies that we've done, it's very close to what the result between 2 surgeons or 2 experts, if they do the manual segmentation and we overlap and we try to calculate the dice, the same measure, we have roughly also 96% between two experts. So from this, now we have the segmentation. and we have the volume, everything. So as I said, the first step for the surgeon is to decide which prosthesis he will use. And for this, they will have to measure everything. So this step is before was fully manually, and they will need to measure at every space of the aorta, the diameters, and if there is thrombus, not thrombus, classification. So here now, what we have more than 500 measurements per patient, done with just one click by the surgeon, and on our software. It takes roughly 10 minutes compared to 1 hour with manual measurements. The main difference also is that between 10 minutes, they can do everything else. They don't have to wait in front of the computer during 10 minutes. And for the quality results, so we've mainly measured the mean absolute error between our software and what they do with some experts. And we have less than 2 millimeters of differences in MAE, which is again very close to what they have in between two surgeons. So we can go further, and also what I didn't say that it also depends of the resolution of the CT scans. So the image, they have size of pixels, of voxels, and so usually it's close to 1 millimeter. So we can't really have hope and accuracy of less than 1 or 2 millimeters, because that's already the resolution of the image we have at the beginning. So this is the final report that we can give to the surgeon, so that they can, from this, select the device they will put into the patient. The main advantage of this solution is that it's faster, and also it's not dependent then it's dependent in the choice of the prosthesis, but it's not dependent on the measurement that they have to do. So now we have the volume, we have the measurements, we can select the prosthesis done by the surgeon, and then we can do the numerical simulation, digital twin of the patient. So here we have 3 main things. The first is that the aorta, as I said, is patient specific. So for each patient, we have a different aorta because of the segmentation. So the shape is different, but the biomedical properties are we use the same for all patients, because we have no way of knowing for each patient if the elasticity of the aorta is different from one for another. We can know that, for example, the thrombus has some specificity, the classification, but in between patients, we won't open the patient to do some measurements and apply this. Then we have the stent graft geometry and materials. So here again, we have some specific material properties depending on the stent, depending on the manufacturer. And then at the end, so we do the finite element deployment simulation of the prosthesis inside the specific aorta. So I've already showed a bit this pipeline, but maybe now you understand a little bit better of how we start from the CT scan and how we merge it directly with the prosthesis to get the simulation. One more complex operation I told you just before was what we call FEVAR operation. So FEVAR is like EVAR, but with the F for fenestrated. So it's like the same kind of prosthesis, but I don't know if we see well and the foundation, but we have some what we can fenestration here, like some window and the prosthesis, so that the blood flow goes into the prosthesis and can continue into all the collateral arteries. So this is due to the fact that in this patient, the aneurysm is a bit too close to the renal artery that we have here. And then if we put the prosthesis here, it's already inside the aneurysm, so it doesn't make sense for a surgeon. So this is why we have those kind of prostheses. And with the simulation, what's already also important is the validation of the simulation. I told you a little bit about the validation of the segmentation. So we have ground truth and we compare. Here, the ground truth will be the post-operative CT scan. So we start from the preoperative, we do segmentation, simulation, and then we compare the simulation with the post-operative CT scan after the operation. And those CT scan, we can see pretty well some what we call markers, or all the metallic parts, sorry, not metal, but of the prosthesis, and then compare it to the simulation that we have. So in this example, we have done two simulations, for instance. One is rigid, which means that the aorta won't move at all. So we consider it rigid. The prosthesis can move, but not the aorta. Sorry. And in this case, if you look at carefully that the proximal, so the top part of the prosthesis, you see that if the simulation is rigid, you have a much more U shape of the stent at the top, which is due to the fact that the aorta can't really move and being bigger due to the force of the stents. And so you can see that the comparison in the shape is closer with the deformable. And here is what they did before having the simulation. Usually they have like 3D printing of the aorta in plastic, which is rigid, and they put physically, not numerically, they put the prosthesis inside, but so the 3D printing can't move, and we have the same U shape on those experiments done in the rigid simulation, which shows that, so we didn't do it on one case, but with many cases. And we show that the numerical simulation is very close to the postoperative CT scan. And so, yeah, that's how we validate at the end the simulation. We've also some simulation, some validation about the position of the fenestration, which in those cases are very important to be sure that they are just aligned with the collateral vessels. So yeah, that's how we've done the validation. So now for the risk-aware planning. So the main risk about those surgeries, there's not just one, but the main one is what we call endoleaks. So endoleaks is just a leak of the blood flow that will be able, by one way or the other, to still go inside the aneurysm and make it grow again. So there are different types of endoleaks. So for instance, the leak can come. So type 1 is going from the top of the bottom of the prosthesis, which means that there is no, the apposition of the prosthesis is not good enough. Maybe the prosthesis is too small, or yeah, those kind of things. And then we have what we call type 2 endoleaks, which means that in some cases, we have, like I showed before, the lumbar artery that are inside the aneurysm, and the blood flow can still going from those small collateral arteries. And so the result is the same. And then we have, so the two first one are the main one that we have. Then we can have some troubles with the prosthesis, some holes, and so we can't really predict that there will be a hole in the prosthesis, but we can predict that the apposition is not good or something like this. So more than 25 patients have those kind of endoleaks, mainly with type 1 and type 2. But still, it means that almost a quarter of the patients will have to be reoperated because the aneurysm will continue to grow after the surgery. So what we have developed based on the digital twin and the numerical simulation is about the type 1. So type 1A, I would say. So it's the blood flow that will continue to go inside the aneurysm from the top of the prosthesis. So the idea that we have here is to analyze every cut done from the simulation directly between the prosthesis and the aorta to see if there is some mismatch in the position, which means that the aorta maybe doesn't touch very well the prosthesis, and there is some space in between. So that we can see, for instance, here we have the prosthesis inside and the aorta here, and we see that, for instance, here there is some gap, so the blood flow can go in and then continue into the aneurysm. So we have developed what we call endoleak risk index, ERI, and the idea is to have a machine learning algorithm based on all the patients that we have. So for sure, it's supervised. So it means that we have many patients. We know if they have developed an endoleak of type 1, and we know the one that didn't. And then we put everything into a machine learning algorithm to be able to predict which patients will develop type 1 or the other. And then the surgeon can decide to maybe change the prosthesis, try another one, simulate with another prosthesis, or maybe change the way he wants to do the surgery. Maybe he here for EVAR with fenestrated, which means the prosthesis will be higher. So the last visual that we show to the surgeon to see the result of the simulation is those kind of results. So we have a low ERI, means that there is almost no risk that the patient will do another leak in 1, 2, 3 years. And also we have some patients with higher ERI, which means that we think, or the algorithm thinks, that there will be another leak in some years. So maybe changing the prosthesis. So we have different factors that can lead to those leaks. But actually, from the perioperative CT scan, at the end, without doing surgery, we can predict if there will be a leak. So the industrial part, I would say. So this is the product that we have today online. So there are two separated things. The first one on the right will be all the sizing parts. So doing all the automatic measurements from the CT scan to be able to select the prosthesis that the surgeon wants to apply. So we have the 3D volume, so it can be so the mesh of the aorta. We have the aneurysm, so in maybe a bit more darker, so the thrombus and the calcification that you see here in white, and then we have all the measurements available depending of what the surgeon wants to do, which place he wants to see, and then the other one. So which is more about the simulation. In the first one, there is no simulation. The second one, once we have selected the prosthesis, we do run the simulation, and we can see the 3D image and the risk there will be a leak on a leak. And the surgeon can run different simulations with different prostheses at different location and see if this risk evolves in one way or in the other, and then adapt the surgery depending of the results of the this. So in this case, for instance, we have very low risk, mainly because what we call the neck, so the place where the prosthesis will be applied at the top is really straight, the same diameter, no angulation. So it's really like the most simple case that they can have. So it's logical that there is no risk, but yeah. So from what we've learned a little bit, the difficulties that we had is the patient viability. So we need to have many patients for the AI parts, mainly the segmentation. As I said, we have roughly 400-500 patients because there is a huge variability in the anatomy of each patient. The computational performance is not easy to do online because we have some AI stuff that runs on GPUs, and also numerical simulation that is more on CPU. So the regulatory pattern, I talked a little bit about this, but this is not easy. The workflow integration inside the hospital is also something that it's not easy to achieve, because today we have our online platform, but to export the images from the hospital to this platform is not always easy because of the format and the packs and everything inside the hospital is pretty constrained. We try to keep as much as possible the explainability of what we developed, mainly in AI, not necessarily in the segmentation, because we can see the results and compare, so it's easy. But for the underlying risk index, for instance, we need to give surgeons some ideas of why we decided that it's a risk on a risk, and then they can trust us on that. And also data governance, we take care of this because it's medical imaging, so we can't do everything we want with the images. A small overview of what we do apart from the aorta. So we do simulations in all cardiovascular fields. We have some mitral valve segmentations and simulations, so about the cardiac parts and valves. We have the carotid. So in this case, in the carotid, it's more like stenosis. So it's like the reverse of the aneurysm. It's the carotid becomes too small, and then they put stents to extend it a little bit more. And the same applies also for all inferior members. So in the legs mainly, it's the same like stenosis, and we can put also some sets. So just to say that in the cardiovascular field, numerical simulation has a lot to do. It's then with different pathologies, and so yeah, we can play a long time with all the simulation that we could take care. And finally, maybe some 3 messages that I wanted to push is that today we already apply at the same time AI and physics-based simulations, and it's really complementary. I know that there are some improvements and use AI to do the numerical simulations. And today, what we have seen is that AI is very good, but when you have like few patients, applying AI to learn a numerical simulation on just a few patients is very difficult. So today, for me, it's really like complementary, and there is almost no one doing this apart from us in this field. Maybe in other fields there are, but we don't have any competitor on those 2 technologies actually. The digital twin turn the simulation into really interpretable and risk-aware decisions. That means that from the image, we are able to predict a little bit the future of the operation and to help surgeons deciding what he will do for the surgery. And the first one is the industrial development that makes it really usable. I mean, we can have the best product, the best technology of the world. If you don't have industrial deployment that allows everyone to use it, then you don't have any impact. And today we have almost 10 years of existence, and we spent the first few years at developing really something very good, very perfect. And now we see that going into the market and selling and make it easy for the user is not also an easy task. So yeah, that's the last point that I wanted to share. So yeah, thank you. If you have any questions. That was clear.
Allô, allô.
Quand vous avez parlé des erreurs moyennes qui sont faites par... et vous l'avez comparé aussi aux erreurs dans des experts.
Oui.
Alors, j'ai 2 questions. Une est, si vous pouvez cartographier où les erreurs sont faites, est-ce que les experts et le système, l'AI font les mêmes erreurs? Et la deuxième question est... j'imagine qu'il y a des experts qui sont plus experts que les autres. Et donc, c'est où que votre moyenne se place par rapport aux meilleurs experts?
Alors, ce qu'on a fait du coup, effectivement, sur l'étude, on avait pris... sorry, in English, sorry. du coup, j'enchaînais. So, for the city, we took 4 surgeons. 2 were juniors and 2 seniors. One was more senior than the other. So we took it at the reference because we think that it's the best that we can have. And actually, so we saw that in between senior and juniors, there are more differences than between seniors, so which makes it logical. And so for the question about where does the error is coming, actually it's more depending on not the experience, but more what the habits actually. So some of them will, for instance, if I go back, maybe some slices we can see there. So here we do some measurements. So we have, as I said, we have 3 parts: the lumen, the thrombus that we don't here, and the classification. So it also depends on what they do for the measurements. If they really measure the classification, for instance, because the idea is to do the measurements to put to to find the prosthesis, the diameter of the prosthesis, the length of the prosthesis, to put it in the patient. So some surgeons have, from what they did, they think that it's really good to include, for instance, classification inside the diameter to have the diameter of the prosthesis. Some of them think that using the classification, since it's very rigid, we don't need to measure this. So it's more, we don't have like a really specific error each time. It's more dependent of the surgeons, what they are familiar with it. And actually, so the design that we took is more to be a bit inside those. So taking, as you can see here, taking a little bit the classification, but not too much. So we try to have like a small standard in between all the, we took all the opinion of all surgeons and trying to do an average of this. So that's why we have almost the same differences that in between surgeons, because we try to do the mean of this. But that's a difficult question because each surgeon has his method, and if we change it, maybe they won't like it, or so.
Thank you.
Thank you for the presentation. I was wondering, since your product is data dependent and your entry point is you collect like the CT scan to do the segmentation, 3D reconstruction, are you allowed to retain it to in the future, maybe improve your models or keep, or how does it work?
That's a good question. I guess it depends on the country or where you're developing.
Okay.
But here in France, to have the images to improve your model, to train it, you have to ask to the patients if you have the right or not to use it. So mostly we have some clinical studies where the patient is aware that his data will be used for training something, training a product, some tests, etc. So on those patients, we can keep the images and improve it. For the routine procedures, the products, we are not allowed to do it. So we have the images. We can just analyze if the segmentation is good or not, if the result is good or not, based on what we think. But we can't use directly the image to relearn something.
Okay. Thank you.
So that's a bit of pity, but, but that's the way it is. And mainly for deep learning and everything, really the data is the most difficult part to have, and because today you have plenty of models that are working well. The only thing that you need is data, and annotated good data and annotated data.
Yeah, hello. Thank you for your presentation. What you have done so far is amazing. So I was wondering now, what are the next steps, your new objectives or challenges?
Okay, thank you. So there are, as I said, yeah, there are many things for the numerical simulation presented at the end. So all the fields that we can have apart from the aorta. If we're talking mainly about the aorta, I would say that the first step for us is going into other countries like USA. So that's it's not technical point, but for the company, it's a really a strong things that we were trying to achieve. And then, so in the aorta for the simulation, what we don't today take too much into account. So we take the classification into account, but not really the thrombus as it should be. So it means that we do, as you can see here, maybe here. So the part in red is the lumen, so the part where the blood flow is coming, and we can adapt the properties of the mesh depending if there is classification of thrombus. But thrombus is really like a volume part, and that can be compressed. So in the numerical point of view, we have some progress to do on this part to really simulate. For instance, here we can really see the thrombus here, and if the operation goes well, the thrombus will retract, the volume will decrease, and we don't simulate those kind of things. So I think it's important for the surgeons also not just to see if there is a risk, but also in 2 or 3, 4 years, is the volume will reduce and then prevent some risk. So Yeah, I would say that in numerical simulation, that's the new technology that we try to achieve.
Another question? Someone? No? So thank you, Florian.
Thank you.
Kylian?